Hi everyone, and welcome to our seminar. Today, Ali Vakilian is going to give a talk for us. Ali is currently a postdoc at the Ideal Institute hosted by TTIC. Ali got his PhD from MIT under the supervision of Eric Demain and Piotr Indik, and his research interests include learning-based algorithms, algorithmic fairness, and algorithms for massive data. And today, Ali is going to tell us about approximation algorithms for fair clustering. Ali, it's all yours now.
Hello, everyone, and thanks for the introduction and having me here today. So as Said said, I'm going to talk about approximation algorithms for fair clustering. So before that, let me make sure that my slides are moving. So they're moving, right? Okay, cool. Okay, so as algorithms and machine learning are used widely in different applications, they're also taking over humans' role in making high-stake decisions. So decisions that can greatly impact our lives. For example, you can think of approving loan applications where algorithms are used in deciding about these applications, or in hiring decision where they're used in the hiring process, which includes both on how a job opening is advertised, who are the target audience, and how an automated resume screening software selects potential applicants. Or in college admission, where the goal for algorithm is to measure and predict the student's success. Or in the criminal justice, where algorithms are used in wide range from determining policing strategy, pretrial risk assessment, or recidivism prediction. So they are all over in many important applications. And while algorithms' decision-making are often way more efficient, faster, and even more robust than humans, concerns have raised about the fairness and justice of the decisions made by algorithms. For example, there are well-known instances in the press where an automated decision-making process has made discrimination against certain individuals or groups of people. You have seen lots of them in the news, and just to give you some example, it was in a report in ProPublica that strong evidences show that the computer program that were used to predict the likelihood of each prisoner committing a future crime was discriminating by race. Or in a recent audit by a team in USC, it was shown that the ad targeting system in one of the tech companies discriminates certain protected groups characterized by gender and race. Okay, and there are many other instances. And the bottom line is that we have strong evidences that in many cases, algorithms discriminate against certain individuals or groups of people. And this basically indicates that we need to explicitly take care of fairness when we design algorithm. And it's not something that we can have for granted and just instead try to go and do our usual job of design when we are designing algorithm. Okay, so more precisely, in classical algorithm design paradigm, the focus is mostly on optimizing either the accuracy, running time, or space usage, or something similar along this line. However, the way users interact with algorithm is different, and outcomes of algorithm may have significant impacts on users' life. So they do see other aspects of the output they receive from algorithms as well. It's not just about how long it takes for them to receive an answer or some measure like this. The actual outcome may have a significant impact on users' life. And this concerns has motivated an extensive line of research on fairness, and by now has created a very active research community on this topic, just including this TOC for Fairness project. And so that's by now we have lots of interesting results, and and observations about how to just take care of fairness and what exactly it means to be fair. Okay, and the topic that I'm going to talk about today is fairness for clustering. And the clustering problem itself arguably is one of the most important tasks in unsupervised learning and even in algorithm design. And due to its wide application, it's a natural choice for fairness investigation. And in fact, it was one of the first problems studied under fairness constraint. So just to give some overview and what we know about this problem. So it was first introduced in the work of Chiriachetti, Kumar, Lattanzi, and Vasilevsky. And the way that they defined the fairness was with respect to disparate impact doctrine. So they wanted that come up with a partitioning of the point set such that each cluster has a proportional representation of groups, different groups. So basically, right. So basically, the idea is that we want to select individuals into multiple categories where each category has some associated benefits or harm, you can think. And basically, the balance of the cluster basically asks that different groups receive those benefit or harm in similar proportion. And yeah, and in other words, I mean, we would like to have restricted dominance in each cluster and also minority protection in each cluster. So let's see then a very simple example. Suppose here, these are the points that we would like to cluster, and we would like to partition them into two groups. Then if we have no constraint and we have no idea whether the points are, and if they're coming from different groups or if they're all from the same groups or some information like this, then the natural clustering is will look like this. Even if we consider the distance-based objective, this looks to be a very good solution of clustering. However, in many cases, we have much more information about the data points. And for instance, we know that they're coming from different groups, or they have other meanings than just a point in this space. So for instance, here, if let's say we have a blue points and red point, and then if we would like to ensure the balance in the clustering, the two clustering that we construct, then a good clustering looks like this. So it's very complete. It has a completely different structure rather than the two clustering that we saw without this group information. And even the cost is different, so the clusters themselves are different. So basically, to ensure the fairness, we would like to, in some sense, solve a new problem. And we would like to just take into account this new constraint and come up with a new algorithm to take care of this fairness requirement. Okay, and let me just give some motivation. So basically, the main motivation for this notion, as in the work of Chiriachetti et al., was basically with respect to the application of clustering in a ML pipeline. So where, for instance, you would like to augment each example in a data set with the index of the cluster it belongs to. So basically, they usually do that to give some expressiveness power of the data and augment the points. Okay, and you can also think of different applications, like if you want to aggregate data and you would like that for the data that aggregated in each cluster is not going to make some statistical bias against certain groups. Okay. And as I mentioned, clustering, I mean, has different application, and you can think of it in different contexts. And for that reason, people have also studied it from different angles. So if you think of data summarization with application of clustering, where you would like to come up with a fair representation of different population when you are clustering. So that's a different way of thinking about clustering. Or if you think about the facility allocation type applications of clustering, where you would like to open some facility to serve different population and individual fairly. So that's also another application you can think of. So I will briefly talk about this the other context as well, but let me start with the first notion here. Okay, so this is what I'm going to talk about. So I'm mostly going to talk about clustering with group fairness. So with group fairness requirement, where basically we require that any group, and in particular protected group characterized by race, gender, or other sensitive attributes should be treated similarly as as an advantaged group. So, and then under this notion of fairness, I consider the balanced cluster requirement and equitable representation requirement. So let me start with balanced cluster notion. So this is basically the definition that I described, introduced by Chiriachetti et al. And to make it formal, let's this is how we define. So we are given a collection of endpoints in a d-dimensional Euclidean space. And we assume that each point is colored either red or blue. And then we say we would like to construct a balanced clustering, and we say our requirement is that each cluster must be R and B balanced, which means that the ratio between the red points in each cluster to the blue points in each cluster be between R over B and B over R. So basically, we don't want any color class dominates in any clusters. Okay, so we would like to have a fair representation of each color class in all clusters. Okay, for instance, this is an example of 3 and 2 balanced clustering. So we have the ratio between red and blue in each cluster is between 3 over 2 and 2 over 3. Depends on how you look at the ratio. Okay, and the problem that we are considering here is RB fair K median, where the goal is to partition the point into K RB balanced cluster such that the average distance of points to their centers is minimized. Okay, so that the average distance part is just the K median objective function. Okay, so the problem was studied first by Chiriachetti et al. And the way that the design algorithm for this notion of fair clustering was through an object. They call it fairlet. And fairlet is defined to be the minimal sets that satisfy the RB balance requirement. So by the minimal, I mean that you cannot decompose the fairlet into smaller fairlets such that both are still satisfying the RB balance requirement. I mean, this is a very simple example, but here is a one-on-one balanced fairlet decomposition of the points that we have. So we have decomposed all points into one-on-one balanced fairlets. Okay. And then a notion that is important here is the fairlet cost, where basically means what's the total distance of points, which means that in a given fairlet, what's the total distance of the points in the fairlet to their centers that we have picked in the fairlet, and that center you can think of some point arbitrarily in the fairlet. So for instance, if this is the fairlet, then the total sum of these two distances is the cost of this fairlet. Okay, and then they come up with a very simple to state but very clever algorithm for fair clustering, and it's somehow very fairly general algorithm. So they say that, okay, first we compute an approximately optimal fairlet decomposition of the points. Okay, and then once we have those fairlet, we just consider their centers and then cluster the center of the fairlet into K groups. And for that, I mean, we can just use one of the existing, let's say, K median algorithm that we have. Okay, and then they prove that this algorithm will give us order alpha plus beta approximation for the fair clustering problem. Okay, so if we have an alpha approximation for the Fairlight decomposition part and the beta approximation for the clustering, just if you have beta approximation for one of the clustering algorithm that we're using, then the overall algorithm is order of alpha plus beta. And why it's nice? Because first, I mean, they show that you can get a constant factor approximation for the Fairlight decomposition part. Since we have different constant factor approximation for this clustering problem, overall, we get a constant factor approximation for fair clustering. And so that's very nice. However, I mean, there are two limitations that I'm trying to address in this talk briefly. So one is that the running time for the algorithm in step one, which is Fairlight decomposition, is at least quadratic. So basically, their approach is working via max flow computation on instances of on large instances, and if you compute the runtime, I mean, it at least need a quadratic time. So this is one thing, and you hopefully would like to have something near to linear time or faster if possible. And the other part is that as they were introducing this notion, I mean, their algorithm only works for t and 1 balanced, and where t is an integer. So you cannot have all, I mean, you have better all possible accuracy and get more accurate balanced clustering if this is something that you're looking for. Okay, so, and as I mentioned, I'm trying to, what we showed was a near linear time for a decomposition algorithm. So, and our approach was by using a technique in the metric embedding that we embed the points into a tree metric called HST. And so just let me tell you what HST is very in high level. So when we say that we use the, we embed the point into this HST tree, HST where basically there are stands for the hierarchically well separated tree. So then is that, I mean, we would like to embed the point into HST, and basically we would like to embed them into the leaves of this tree. And this tree has several nice property. For instance, if we look at any point in this tree, the edge lengths of these nodes to its children are all equal. For instance, here, I mean, if you look at they're both 1/8. And the other one is that when you start from the root and going to some leaf, I mean, the edge lengths are decreasing by a factor of 2. At least by a factor of 2. Okay, and this is basically, this is called 2HST. You can think of larger factors as well. And then instead of decreasing by a factor of 2, they decrease by a larger factor. Okay, so that's the high level description of HST, and let's see how it exactly helping us here. So, and the way we construct the HST, since we are looking at the Euclidean case, we do it by imposing randomly shifted grid over the data. So we start with the whole data points in the root, and then we impose a randomly shifted grid over the data, and then we put each subcells or each grid as a child of the vertex that we were start from. Okay, like this. And the edge lengths are basically proportional to the diameter of these cells. Okay, and then, I mean, we continue this procedure recursively with grid of a smaller size until each cell contain at most 1 point, or the cell size becomes small enough. So for instance, here we have only 1 point, we stop at this point, but for the rest we just continue. Okay, and then we will have a tree representation of the data points as I promised. And now this also has the nice property that I mentioned. It's not hard to see that, and we know that the distortion of the distances are also small. I mean, are bounded. It depends if you count it as small or not. Okay, so now now that I described how we construct this HST embedding of the point, let's see how our algorithm works. So once we have this embedding, then we just go with a top-down traversal and greedily construct the fellets. That's a very simple and fast algorithm. So for instance, consider one-on-one balanced case. In this case, we start with the root, and then we check if any of its children are unbalanced. So we start from here. I mean, we have 2 red and 2 blue. It's balanced, so it's okay. We know that we can delegate the task of fairlet composition for the points in this subtree to the subtree itself. We don't need to help with fairlet construction here. But here, I mean, we only have single blue points, so we need to do something with that because the subtree itself cannot make a fairlet itself. So we just hypothetically move the blue points to the root as if that we are going to take care of it. And then we go to the next subtree. Then here we have more red points than blue point. And then we just arbitrarily think of moving one of the red points to the root, again, hypothetically. And then we continue, and the last one is also balance itself, so we don't need to do anything here. And then once we are here at the root, then we can just construct a fairlet with the points that we have here, and then recurse on the children. Okay, that was a very simple description. I mean, there is a caveat here. I mean, when I'm considering one-on-one balance case, the set of must have set in the root, or the set of leftover basically points from the children themselves are balanced. Okay, so for instance, here we have exactly 1 blue point and one blue point and 1 red point. But it may not be the case if we look at the other more general RMB balanced case. For instance, let's see an example for 2-on-1. So here, this is 2-on-1 balanced. This is not. This is 2-on-1 balanced again. And this subtree is also 2-on-1 balanced. And as you see, we do not have enough points here in the root to construct a 2-on-1 fairlet anymore. So for that reason, I mean, we may need to borrow points from the children, although they are completely fair and they can take care of the fairlet construction themselves. And then this required to come up with more careful analysis of the cost and how we can charge the cost of the fairlet that we are constructing at each level to the optimal cost. Okay, so but I'm not going to talk about the details, and that's the result that we get. So we will have an order of d log n approximation for fairlet decomposition in time order d times n times log n, and you can I mean, you can get rid of the d and get something like a log n if d is much larger than log n via some JL dimensional reduction. But that's our result, and as I mentioned, I mean, this run is near linear time, and it works for all values of RMB for the notion of balance. And in fact, this works very well in practice. So in compare, for instance, to the constant factor approximation that Chirichetti et al. Proposed, I mean, our fairlet costs are comparable, and even in cases that are, I mean, they're much, they have better cost. And I mean, more importantly, I mean, it can handle up to several millions of points rather than, I mean, just very simple CPU, so nothing fancy, rather than the thousands of the point that could be handled by that max flow type of algorithm.
Can I ask a question, Ali?
Sure.
So where does this approximation factor show up? Like,
so you mean d log n?
Yeah.
Oh, okay. It's, yeah, I was hiding because it's just because of the metric embedding part. we embed to HST. So that's the distortion we get from the metric embedding part.
I see. So there is some distortion function defined.
Yeah.
The approximation factor is
Yeah,
there.
exactly. Yeah, exactly. Because as I'm, as I'm embedding the point, right? Now the distance, for instance, between, I don't know, this point to this point is something like going through the root to come here, right? But they're very close to each other here, as you see. So, and we know that, I mean, the distortion is something like order of log n and d log n if you just consider this shifted grid thing.
Okay, so the edges on this tree actually mean something, which is the length.
Yeah, exactly, exactly. So the edges are proportional to this diameter of the cells. So for instance, these edges are basically equal to diameter of these cells, which are all equal.
I see, I see. Okay.
And as you go, I mean, further, deeper in the tree, I mean, they become smaller by a factor of 2.
Okay. Okay, thanks.
So yeah, sure. Thanks for the question. Okay. Yeah. Okay. And there were also more recent result on this notion. I mean, people have studied multiple groups as well. So in the algorithm that I describe it, we only consider 2 groups, or in the previous work of Chirichetti et al., they only consider 2 groups, but there was several nice results that could handle multiple groups. And they could also work with both a relaxed type of fairness, that we would like the fraction of point in each group to between given parameter beta I and alpha I, or they were working with the exact fairness, where we would like to have exactly the same balance as the whole population in each cluster. And as we are considering the clustering, so I mean, one important tools for coming up with a scalable algorithm for clustering is corsets, and it also have been investigated in several work, and they have come up with a very efficient corset construction for clustering as well. Okay, so if there is any question, I would be happy to take. Otherwise, I will go to the next notion that I wanted to consider. Okay. Okay, so that was about the balanced cluster, but there are other applications you can think of that may need different notions, a notion of fairness. And in particular, I'm going to talk about the socially fair clustering, which was introduced by independently and very recently by Qadiri, Samadi Vempala, and Abbasi, Bhaskara, Suresh. Okay, and their idea and motivation was, okay, rather than having just balanced cluster, in cases, there are also some need for assuring equitable representation. Okay, and this is when you can think of somehow clustering as data summarization, and you would like to make sure that in the summarization that you provide, each demographic group is well represented. And what's the measure of representation for points in a clustering is usually the cost, right? So how we measure the optimality of clustering is usually via the cost. For instance, if you look at the k-median, k-means, or this is one way of measuring the well representation of the points. And now their idea is that, okay, I would like to come up with a clustering such that if I look at each group separately, they have this feeling that their representation are fair, or they have almost, I mean, we are not harming one of the group in expense of just giving benefits to the other group. So let me see, to example and give more examples as well. So if we look at if we try to minimize, for instance, let's say k-median cost, this would be a reasonable thing to do for 2 clustering. Or even if we would like to have to guarantee the balanced criteria that I described, this looks very reasonable, right? However, if you seek, if you be careful here, so the cost for the blue points in all clusters are much smaller than the red points. So basically, red point may feel that, okay, they're not very well represented by the centers that have been picked. And they may claim, I mean, they would like to say, okay, something like this is more fair. I mean, we all having the relatively equal cost to our centers, which is basically is what's important in clustering. Okay, and why it's matter? For instance, if you would like, if you consider the examples like where to open vaccination site or where to open the polling stations. So then different group would like to have the same sort of access to these facilities, right? And or you can think of, for instance, clustering is used as a guideline for allocating patrol services to each area or cluster. And then again, each group would like to have the same cost to these services. Yeah, and that was basically the type of motivation that they had. And just to avoid the trivial solution, because if you only want to guarantee that every group have the same sort of cost to reaching their centers, then there is a trivial solution, right? You can just pick very bad centers for everyone. So then everyone had to go along, how to go long distance to reach their centers, right? So then to just avoid this trivial solution, we would like to have some global objective, just to make it to make it reasonable statement. So, and the idea for the objective function is to minimize the maximum cost across the groups. So let me be more formal. So let's assume we have a collection of endpoints in a metric space. It doesn't have to be a Euclidean anymore. And then also let's assume that we have L groups in this matrix. The points are coming from L different groups. L can be much larger than 2 here. So they're denoted as P1 to PL. And then think of a clustering cost objective. You can think of, for instance, K-means, K-median, or other distance-based objective. And then the goal is to find a K clustering of points that minimizes the maximum of the given clustering cost over all group. So for instance, for the socially fair K means, the goal is to find K centers, C1, CK, such that if you look at the average distance of square distance of point to their closest center, the maximum of this value is minimized.
Is there any reason to consider the square distance instead of the?
No. You can think of K median. Yeah, you can think of any. Actually, our result holds for any LP LP cost function, LP norm cost function. Yeah, but K means, I mean, it's a very natural objective for the clustering, for instance. Okay, and just to give other way of thinking of this fairness, I mean, this notion of fairness was previously studied, for instance, in the context of PCA, and the goal was again to minimize the maximum average reconstruction loss for different groups. So this is basically, I mean, very reasonable notion that you can think of many problems that you have different groups, and you would like to make sure that the cost of none of them is going to be ridiculously larger than anyone else. So you would like to have somehow minimize the maximum cost over all groups. Okay, and so that was for the notion of fairness, that is to minimize the maximum cost in some sense. And it was first, as I mentioned, studied in the context of clustering by two groups of people. And in the work by Qadiri et al., they came up with a fair variance of Lloyd's algorithm, which is a very practical algorithm for k-means. And then they show that their algorithm is going to achieve order of L approximation for fair k-means, where L is the number of groups. And in the other work, I mean, the parallel work, the independent work by Abbasi et al., they also achieve order of L approximation for fair k-means and fair k-median. And besides, they also achieve by criteria approximation, where they could show that if you pick a 2K center, you can get a cost within at most 2 times the optimal K clustering. Okay, and this is our result with Yuri Makarichev. We show that we can get e to the order p times log L over log L approximation for socially fair LP clustering with arbitrary weight function and possibly overlapping groups. Okay, so I'm setting it's very general, in a more general setting, but what you can think of is just basically, you can think of the case for k-means, if you would like, I mean, to compare. Then it's exponentially improve upon the order of L approximation of the previous work and get order of log L over log L. And this is the approximation we get for k-median and k-means, and actually it works for more general LP function, LP cost function. And we don't need also to have just look at the average cost. We may want to pick the weight function differently. That we still get our algorithm still works in this setting. And actually, I mean, the groups can be overlapping. They don't need to be disjoint. Okay, so let's give some technical details. Hopefully it will be short. And then that would be basically conclude the talk. Okay, so what's natural thing to do for the k-median or k-means? I mean, if you're familiar with this approximation algorithm for k-median, for instance, or k-means, I mean, the natural way is just to solve it via LP relaxation and then solve the LP and then round the solution to an integral one. And this is a natural, for instance, LP relaxation for this problem. So here we define a variable yv for each point, which basically denotes whether the point V is a center or not. So yv is equal to 1 if V is a center and 0 otherwise. And then we have that we would like to pick at most K center, right? So that's the constraint that we have. And then we also define x of uv to denote whether the point U is assigned to center V or not. Okay, and then we would like to make sure that all points are assigned to a center that we have picked. So we would like to have x of uv, sum over x of uv over v is equal to 1. And then, of course, we would like to make sure that a point U is assigned to center V only if V is a center. Okay, so that's a very standard relaxation. And in fact, that was the approach that was also considered by Abbasi et al. And how they got their order of L approximation. And in fact, they show that the integrality gap for this LP relaxation is omega of L, and that's why they couldn't get better than order L approximation. And our yeah, okay, just for simplicity, I just here I define the LP relaxation in the general LP norm function, but you can just for simplicity think of the k-means here, and then p is equal to 2. So in the rest, I will just assume that p is equal to 2. So to make it more a bit simpler. And now our goal is to basically come up with a new LP relaxation, or better, or more precisely, we would like to just strengthening this LP relaxation so that we can get rid of this integrality gap that they prove. Okay. And for that, I mean, we need to have some observation about how the optimal solution look like, and what we know more about the structure of the optimal solution, for instance. Okay, for that I need to set up a few notations here. So one thing is that I look at the ball of radius r around point V. So basically it denotes the set of points in P that are at distance at most r from V. And then another notion that is a bit tricky is the volume of the point, the ball of V with radius r. And I also say volume of V at r, which is basically the r square times the maximum over the weights of different group of the points in this ball. Let's see an example because it's easier to see. So this is the ball of radius r around V. And then let's assume that the weights of all points is equal to 1. Okay. And now we have 3 blue points and 5 red points. Then the volume of this ball is basically the maximum over the total weight of different group, which here is 5, because the total weight of blue points are 3 and the red points are 5. And so the volume of this ball is 5 times r squared. So why it makes sense, or why it can help us? Because if I know that for every point u in this ball, the distance of u to its closest center is at least r, then it means that the cost of clustering, the current clustering that we're considering with the center set of center C is at least volume of V at R. This is exactly this definition, right? So basically this ball is somehow a witness ball for cost of volume V at R. This is some witness that's showing that the clustering cost is at least volume of V at R. And then to use this notion, I mean, we consider a threshold Z, which basically is our guess of the optimal clustering cost. So we guess, for instance, the clustering cost is Z. Then we define delta Z of V for each point V as the minimum radius that you need to go such that your volume is larger than Z. So why it makes sense? Because basically there are the set of potential witness ball for cost Z. So if you are not sure if the cost is Z or not, you can look at this ball and check whether you get a witness, whether you have a witness for that cost or not. Okay, so let's see why it's important, those are notions, and let's see how we can use them to prove something and show some meaningful constraint for the optimal solution. Okay, so let C star be an optimal solution for socially fair k-means of cost Z star. Okay, and let Z be some guess larger than Z star. Then for every point V with non-zero weight, so I'm saying non-zero weight because if it's a zero weight, you can just ignore it. So for every non-trivial point in the point set, the distance of V to C star is less than 2 times delta Z of V. So basically to say that the distance of points to its closest center in the optimal solution cannot be much larger to some value in terms of Z. That is function of Z. Okay, so let's see why it's the case. So suppose this doesn't hold. Then there exists a point V such that the distance of V to its closest center is larger than 2 times capital R, where capital R is, I define it to be delta Z of V. Okay, so I assume that this doesn't hold. So it means that the distance of V to C star of V is larger than 2R, 2 capital R. And now the claim one is that for every point in this ball, the ball of radius R around V, for every point in this ball, the distance of point U to its closest center is at least R, capital R. Because otherwise, by triangle inequality, the distance of V to C star UV would be less than 2R, which is a contradiction because we assume that the distance of V to its closest neighbor is larger than 2R. Okay, so then basically now I use this notion here, right? So now I have for every point here, the distance of the point to its closest neighbor is larger than capital R. So we have that. So this ball itself and the points that are contained in this ball shows that the clustering cost using C star is larger than Z. And we know that Z is at least Z star. So it's a contradiction. Okay. So basically, it means that for every point, the distance of V to C star should be less than 2 times delta Z of. And that's exactly the constraint would help us to strengthening our LP relaxation. And we are going to add this to that natural LP relaxation. And we show that we can now round the fractional solution so that we get the approximation that I promised, the approximation factor that I promised. Okay. So here I show that for every point, for every center V that is further from 2 times delta Z of U from U, U for sure is not going to be assigned to V. That's basically what it means. And you don't need to only consider 2. You can think of any lambda greater than 2. And actually for technical reason, we need that as well. Okay. So then that's how our algorithm works. Basically, now we have this cluster LP that I defined, and we need to just round this the solution to get the order of log L approximation solution that I mentioned. So just to give a note here, I mean, we need to start with a good estimate of the optimal cost, Z star, because our cost will depend on Z as well, our guess of the optimal cost. And that's easy to fix because we can start with a weaker estimate, an order L estimate, and that's easy to achieve by just considering the k-means constraint and ignoring the fairness constraint, and then do a binary search such that we get a good estimate of C star. And that will only increase the runtime by a factor of P log P plus log L, which is very small, or it's the polynomial at least. Okay, so and then the algorithm is as follows. We first find an optimal fractional solution of cluster LP, which is solvable, and then follow the simplify and round framework of Charikar et al. For k-median. We just adopted this framework to this more general objective function and round the solution to get our order log L over log L approximation. Yeah, I'm not going to mention many details here, but just to give very high-level overview of the rounding approach. So they first construct, so given a fractional solution, they first construct a 9 over, I mean, we first construct a 9 over 10th restricted solution, where a restricted solution, a 9/10 restricted solution is a solution in which all points are either open partially with with value at least 9 over 10, or they are closed. Okay, so basically all y values are either 9 over 10 or equal to 0. So this is the restricted solution. And I mean, for that, we need to deal with a more general LP relaxation rather than the standard LP relaxation, the cluster LP as I mentioned. And also we need to work with a more general objective function. And then once we have this restricted solution, the next step is to round this solution. And just if you are familiar with the work of Charikar et al., the way that they did the rounding was via a simple and very clever deterministic greedy approach, where they just sort the points in a greedy fashion and pick the points to the centers, pick the point as a center for the solution. However, we cannot use this this algorithm because we have L different groups, and we would like to preserve the cost with respect to L different groups simultaneously, and we cannot follow this deterministic approach. And basically, our approach is a randomized rounding, so that we can show that all distances are preserved with high probability. All distances over different groups are preserved with high probability. And this rounding also crucially relies on the further structure that guaranteed by the constraint we added for cluster LP. Okay, so that's more detailed, but probably I would like just to skip. So first we consolidate the locations. So basically, which is about just moving around the weights of the points. And in the second step, we move around the open centers to the point that only have non-zero weights. So basically, in the first step, we simplify the instance. And from the initial points at P, we get points at P prime. And there are nice properties here that a good fractional solution here is also a good fractional solution here. And also if we have a good integral solution here, we can convert it to a good integral solution here. And by a good, I mean, the constant, we are losing only constant factors in each of these directions. Okay, and then we have this rounding part that I'm not going to describe in details. If you are interested, please see the paper. But I mean, they have two, but again, if you're familiar with the cherry car framework, our first step is similar to them when we deterministically add a subset of points to the center. And then the next step is to do a randomized rounding. And then we show that in the randomized rounding that we proposed, the number of centers that are picked at the end is at most k, and the cost will be preserved up to a factor of log L over log L. Okay, and further, I mean, we got the approximation factor that I promised, log L over log L. And in fact, we show that the integrality gap of the LP relaxation we propose is also omega of log L over log L. So basically, we cannot hope to get anything better using this LP relaxation. So either you should think of different relaxation or even a completely different approach, maybe combinatorial approach can work better here. And we also have some by criteria approximation, similar to that proposed by Abbasi et al. And basically the idea here is that once you have a restricted solution, you can just settle there and pick everything that you have a non-zero values as a center and get a by criteria approximation. Okay, so what are the interesting questions for this problem? I think are naturally is there, for instance, a constant factor approximation for this problem with respect to L groups? And there are reason to believe that there is constant factor approximation, as for instance, I mean, for any version of K clustering, we have constant factor approximation. And that makes us believe maybe there's a way to get to constant, but it requires, I mean, new ideas. And the other interesting question is, as I mentioned, the work of Qadiri et al., they propose a fair variance of Loi's algorithm for fair K-means. And the Loi's is a very practical algorithm for clustering. So I think it's very interesting to see if one can get better than order L approximation via the fair Loi's algorithm they propose, or if we can propose a fair variance of this Loi's algorithm that achieve approximation better than order L. And then the other thing is, I mean, since we care about the scalability of the result, and the core set is a powerful means to come up with a scalable algorithm. So if we can design core sets for socially fair clustering, that could be also an interesting result. And then, yeah, I would like to thank everyone. And that was what I wanted to talk about. So I guess it's about the time to finish. Yeah.
Yeah, thanks for the great talk.
Sure, thank you.
Do we have any questions for Ali? I have one question. So you said in the feature directions about this O1 approximation, but didn't you say that there is a log L over log L lower bound?
So it's yeah, that's a good question. So that was the integrality gap for that LP relaxation we proposed. But you may come up with, for instance, a different LP relaxation that doesn't have this integrality gap. Or you can think of a combinatorial way of solving it and get it.
Okay.
transfer factor approximation. Yeah, there
And
could be. Yeah.
like another question, like the approximation factor is growing with log L, but the runtime is still polynomial in L, right?
Yes. Yes.
Okay.
Yeah. Yeah. Exactly.
Okay. And also in the first part of your talk, you had this notion that had two parameters, R and B, which means the ratio of red over blue is between R over B and B over R. Is there any reason to have like these two parameters instead of having like one gamma and saying that the ratio is between gamma and 1 over gamma? I wonder if there is any like.
Yeah, I mean yeah, because we rely on this R and B when we are constructing the fairlets. So basically, that's how we make sure that the fairlets are they have enough of each point, each color. Yeah, but I'm sure that it's not something very very crucial, because for instance there are other works that they do not need this, and they only work with the ratios.
I see.
And
okay.
It may be the case that even our algorithm can, with more careful analysis, we can just state it in that. I mean, it's not, I would not be surprised if we can do it. I mean, yeah. but it's not also very straightforward, at least. It needs some careful consideration.
So are you saying that in that notion, when R and B are both 2, that case is different from the case that R and B are both 1? The ratio
no.
is 1.
No, we always assume that the R and B are the GCD is equal to 1. So basically we cannot simplify them. So when they're both 2, I mean, you can think of 1 and 1.
I see.
Yeah. We always, yeah. There.
Okay.
Yeah.
So if there is no question, yeah, we can end the seminar. Thanks for the wonderful talk, Ali.
Yeah, thank you. Thanks for having me here today.
Okay.